Okay.
Okay, so it's recording right now. Okay, so this is my talk on Linux kernel exploitation. Um, I try to start by going like into the basics and start to slowly get more in depth on uh, specific topics like different mitigation techniques, the different sort of targets to attack, how to approach problems. I go into a few examples from CTFs and how you focus towards competition challenges, and then I sort of go into like a few real world examples of like big kernel exploits that people might know about. So yeah, um, who am I? I feel like Claire probably went over this, but I'll do it again really quick. I'm a CS senior, third year being the competition and development chair for EFSIT, or I guess officer. On Discord or IRC or pretty much any other social media stuff, I'm a Nuke Nuke. That's where most people will find me or probably know me as. I'm really bad at notifications, so if you ever like message me and I don't answer, like all of my apps have like well over 100 notifications usually, so that's probably why it's never anything like personal or anything. So I always try to get better about that. It's just hard. I started at UFSIT doing reverse engineering in my freshman year, and then I kind of switched to Pwn over to summer. And then after I got pretty good, I started doing a lot of Heap stuff mainly, and then I started moving towards browser, and then starting like last semester, I started doing some kernel exploitation and learning how that works. I'm 94th on Pwnable TW, which doesn't seem like much, but it's really hard and it's taken a lot of work to get there. So I hope that someday someone else here is even higher than that. Just a lot of practice and dedication sort of leads there. Also, if you, I'm gonna have the chat open, so if you have any questions or anything, you can definitely hit me in the chat and ask anything about whatever you want to know. Okay, introduction to kernel exploitation. Basically, it is what it sounds like. It's how you exploit the kernel. Um, the kernel is basically this low-level program that runs this sort of lower-level connection between the software and the hardware. Usually, a lot of it that you will do on the kernel focuses on like interrupts, which are hardware or software interrupts, and they basically like stop execution so it can focus on different hardware or do things like that. So it's sort of like your operating system, a little bit lower level than your operating system usually. um I'm going to be focusing on Linux kernel exploitation, but there are other Unix kernels that are open sourced and interesting to look at. One big example is the X and U kernel, which is used in macOS and FreeBSD. They both add their own little twist to how it works, but the general like underlying kernel and file system stuff is pretty much the same. A lot of the stuff involved is drivers, process management, file system management, system calls, and then networking. A lot of socket exploitation is kernel level. Um, like any other program, though, it's made in C and assembly usually, which is a sign that you're going to be finding bugs in it. And also, it's such a massive code base. When you have a code base that's that massive, there's no way that every part works perfectly and works perfectly with each other. But a lot of the bugs we're going to be focusing on are drivers, which are like small little additions and interfaces with the kernel for generally hardware, but you can make drivers for many things. However, the like I said down here, the bugs have much different results than userland bug. Generally, you're not going to be like, oh, cool, I got execution. I'm going to run system bin sh because you can't really do that from the kernel. It doesn't have programs like userland does. So the whole plan of attack is a lot different, and that's one of the things I'm going to be going into, and that's one of the things that was the hardest barrier for me when I got into this. Okay, yeah. The similarities, a lot of the bugs are pretty much the same bugs that you'll find in the userland. Anyone who's like seen about stack overflows or heap overflows, those take place in the kernel too. Use after freeze are very important. Probably the biggest class of like actual usable kernel exploits would be use after freeze, and then race conditions as well. And we don't really talk about those much in Userland, or at least we don't really for a competition sense. I don't think we ever talked about those in any of our like talks or anything, but I'll go into that a little later. Integer overflows and signness issues, as well as type confusion. These all happen in the kernel. Generally the same architectures too. If you're running if you're used to x86 and x64, and you're running a kernel that's built to run on a x86 or x64 hardware CPU and everything, then it's the same architecture, a lot of the same instructions. So if you know how to RE a program in Userland, you'll pretty much be able to transition to the kernel level pretty quickly, I believe. Yeah, the different goals, there's no kernel shell. You're not going to be able to run system bin sh from the kernel, and there's also not even like a kernel user. It's not like the kernel is a SUID program. It's a different ring around all of the other stuff that you actually really use for programs and users. So it's not quite the same attack plan. However, at the kernel level, you can change the permissions of these running processes. You can change permissions that are running at user 100 to running at your user ID 1, and then their root privileges, and those tasks can do whatever they need to do. So all of this is managed at the kernel level. You just can't directly do it to your own execution flow. You have to do it to the task you were running from, which I'll show later. You can read files from the kernel or change file permissions and stuff. A big part of it is like if you have a file that you can't read because it has root privileges, you can change its mode as a kernel and then make it readable by all users. And then even if your kernel like doesn't like read the file, you can read it from your other fork, for example, on Userland, and get it from there, and it'll make it a lot easier on you. The attack surface is a lot different because there's not really standard in and standard out. There's not really arguments when you're running with the kernel. There's two main ways that we'll interface with it that I'll talk about, which are drivers and syscalls. I'll mainly be focusing on drivers, but there's a lot of different ways to interface with the kernel. You can create processes, you can create files, you can go into directories and try to like read files and stuff. These all have some sort of a execution happening at the kernel level, so they're not technically like out of bounds for what you can do in a kernel exploit. Yeah, if anyone here does have any questions or anything, like please let me know too, because it's a bit of a confusing topic and I really want to make sure to clarify everything early on. Okay. A big part of it is getting your environment set up. It's not like a normal program where you're just going to run it like / whatever the program name and then start debugging it. It's like this whole kernel image, and then you're going to have some file system and a few other things you have to put together. I'm going to quickly skim over those, but I'm going to have these slides somewhere where you can read them later on. So if you ever actually do start trying to do some kernel exploit, you can just basically walk through the steps that I show, hopefully. First, you're going to want to build the kernel if they don't give you one. There's this repos that has all of the Linux kernel source online. They have FTP and HTML repos, and they have everything, like very specific versions of all of them through all of time. You can get a kernel from like 2004, probably any version. If you're doing like a CTF, you want to make sure to get the exact same kernel version that they have, because of the fact that you want to make sure that all of the structs are the right size. You want to make sure that everything is relatively predictable. You want to have their environment set up, and you can find that with the command uname. Then you're going to make the kernel, which basically means you just unzip the code, go into that directory, and then you can make all no config to turn off any options. And then there's this thing called menu config that's like a ncurses GUI almost, where you can select a bunch of different options for what you want to have. If you want to have a proc file system, you have to select that option. If you want to be able to run 32-bit binaries, you have to select that option. One way is to use something called def config, which is just default and generally pretty good. The other thing is this guy UAFIO from the CTF team open to all, he created this blog post and he goes through his normal menu config options. And usually I just refer to this because they're relatively good and I've never had any issues. Then to build the kernel, it's like any other make file. You type the word make, but it's going to take a long time. So you can use this -j flag with the nproc to basically just use all of your cores to build this kernel, because it's going to be like a large thing to do, and it's not going to be like an easy task. I'm going to close this because it's being loud. Oh, it doesn't change this window. Okay, perfect. Yeah, go on a walk, get some coffee, do whatever. I think usually it takes me like 10, 15 minutes to build it. I remember on my old computer it took me like 30. I know people that have the Threadripper who can probably build it in like 5 minutes. So it's really not like the biggest deal, but it's big. When you build it, it's going to make a bunch of object files, but there's only 2 that really matter. One of them is called the VM Linux file, which is just the actual full ELF of the whole source code. It's massive, and you can run Rockgadget on it. You can throw it in Ghidra or IDA. It would take a long time, but you can. And then the other thing is this Arch x86 or whatever architecture you're building on, and then /boot/bz image, which is a compressed version of this VM Linux file. And it's compressed in a way so that you can set this as your starting kernel, and it'll kind of uncompress in memory and then like boot from that kernel. So this is what you're actually going to be running, is this BZ image, but it's not easy to read like assembly in. You'd have to use this VM Linux. You're going to want to keep both. And it's because they're so massive. You need a smaller version. Otherwise, it'd be massive to have this kernel file. Yeah, when I said the repos have everything, like these are some of the repos. These go from 4.12 to 11 to like 4.13 something. And they have all of the versions, all of the different compressions. They have the signatures. So like, if you ever like are like, oh, I don't know if I can build this version that I found on this challenge, it's like 3.7. It's really ancient. It's on there. They have everything on there. Okay, so then you're going to have a kernel, but if you run the kernel and there's no file system, it's just going to kind of boot and die. Like there's not really anything it can get it can do. There's no userland processes for you to start running. There's no files, so it'll just kind of be done. But what you can use is this really convenient thing online called BusyBox, which is basically a quick way to build a very small, minimal file system. So if you download it and then just do BusyBox install dot in the directory you're trying to do, it will create bin.sh, it'll create ls, cat, just like the normal commands. And then you're going to make them all executable. So you just do 755 to change all of their permissions so that you can use them. And then the normal way that I normally see it for like CTF challenges is that the file system is archived in something called a CPIO. I do not know what CPIO stands for. But what you can do is you can use this command to archive all of the files into this CPIO archive, and then you'll have this init_ramfs.cpio. And this is just one archive file that you can use with QEMU, which I'm going to go into. Okay, and then you're going to have all your files, and you're going to have all of your kernel, but it still doesn't know what to run when the kernel starts. It's not like bin.sh is the default file that all kernels have to run. So you're going to have to create this file called /init in your file system, and basically you're going to set up your init so that you can like change permissions of some folders so you can use them. You're going to basically have to say what you want to start, like what user you want to start as and what file you want to start. So it's probably going to be like UID, who knows what, like 100, and then bin.sh, so you can start a shell. So like this is also a little bit confusing. Normally people don't make these. These are like not something people usually touch. So I also just ripped this one from this guy's blog. It's fine. A lot of times CTF challenges will give you the init ram fs, so you can basically extract all the files and then just use their init and just change it however you want to, but like generally go off of theirs. Generally for a CTF challenge, they're going to start you as a user, because if you're a root, there's really nothing you can't do. You can just cat the flag and leave. But when you're doing debugging and stuff, you might as well give yourself root permissions in this init file, because otherwise you can't be sure. You can view proc call sims, which I'm going to go into. You can view these logs in dmessage, which basically shows everything that print k prints onto the screen and stuff. I mean, I think you should have root to begin with. I think it'd be a very interesting challenge if they were like, oh, you're already root, but you can't read this file anyway somehow. That'd be cool, but unlikely. And yeah, dmessage is great. Yeah, that is rootkit from Pwnable KR. Now that I think about it, there are examples of that, but it's very specific. I don't think you could do anything else with that challenge besides what they did with it. Yeah, dmessage logs are great for print K, and it'll also show crash errors. So if you're running a program and it crashes, you can use dmessage to view like the register states and where it's egg faulted or anything like that. So that's another amazing tool. How to run the kernel? Well, to run the kernel, we're going to use QEMU. You could also probably boot it in VMware or VirtualBox or a few other things, but QEMU is super lightweight. It's super easy. You can run in your terminal. You could call it from a Python script or a Bash script. It's like the smallest, and it's also open sourced and free. So it's really hard to beat QEMU. So you'd probably create a script like this, where you call the QEMU version for your kernel. You allocate some memory for it to use. You choose your kernel file, which is the BZ image we created. You choose the initial like RAM disk, which we're going to use the CPIO we created. And then you want to put this monitor dev null as well, which I'm going to go into why. No graphic basically means that's not going to pop up a GUI, because the GUI is just going to be a terminal. You don't want your terminal to pop up another terminal. And then you append these options for console equals TTYS0 and then quiet mode, so that it'll boot without a bunch of like log messages, and it'll boot into your terminal that you're running. So when you run QEMU, your standard in and out will be officially inside of this VM you've created. There's other examples on his blog as well, because he has a great blog on just getting these set up. Yeah, that'll start QEMU with your kernel and your file system, and you can go from there. This monitor dev null is important because there's a mode in QEMU called monitor mode, where if you control A and then type C, you'll enter this mode where you can dump all of the memory of the running kernel. So if there's a flag in memory, I mean, if there's like a flag in the file system that you can't read, you could just dump memory until you find that inode and find whatever the flag data. You don't actually have to exploit the kernel at all if you have monitor mode. Yeah, they really did that to us in that CTF, where the whole challenge was to find monitor mode and we didn't remember to look for it. But yeah, so if you're ever making a CTF challenge, you'll probably want to put monitor dev null unless you want people to just dump the whole entire image and take your flag without actually exploiting your kernel at all. Okay, now I'm going to go a little bit into debugging. It's not as easy to debug as like a Userland program, but it's not hard either, actually. You can still use GDB to debug the kernel, and it still has the same addresses and breakpoints and everything as well, so it's not too bad. You're going to use these capital S and lowercase s flags to do this. The capital S makes the debugger, makes the running kernel wait until the GDB attaches before it'll actually start booting. So if you want to like start it and then want to make sure you understand everything that happens as it starts, you want to use the S flag so it pauses and waits for you. And then the lowercase s is just for the GDB stub. And then on GDB, you're going to run target remote localhost : 1234 to attach to your port 1234, which is going to be running the QEMU kernel debugger. And then GDB, if you use GDB, it's the same GDB. You can still set breakpoints. You can still read registers, look at the stack, whatever you want to do. However, the main big difference that's really annoying to me is that because it's running remote, it doesn't have just a info proc mappings file. You can't just like look at all the process mappings and be like, here's the kernel heap, here's the kernel stack for my process, all these things. It's not really there's not really a good way to implement that. So you can't just run VM map and look at all of your permissions and where everything is. It's not that nice. So yeah, I mean, that's not easy. That's not nice. CR4 has all of the stuff for SMAP and SMAP and all of the permissions that I'm going to be getting into. It's possible, but it's not as nice as just VMMap. VMMap would be amazing if QEMU had that. So yeah, just if you have your kernel and you have symbols, you could use this to like view the VM Linux binary as the binary for GDB. I must misspelled that. Okay, so you just do gdb./VM Linux because that's the one that has all of the actual assembly and everything in it. And then target remote :1234 and then C to continue. And then if you break, you can actually break act functions in the kernel because you have the symbols of the actual compiled kernel if you compiled it with symbols. So this VM Linux binary is pretty essential for kernel debugging, but it's definitely possible if you don't have it too. So the problem then comes down to like, where do you actually want to break? Like, there's not like a read or a write function. Like, what stuff where would you even find the like beginning addresses? Because you don't want to throw the whole kernel into like IDA or GDB, into a Ghidra, because it would take a long time. So instead, there's this nice file in the kernel in the operating system for Linux called proc/callsyms, and that just stands for kernel all symbols. And basically, if you have the permissions to view it, which you can have disabled, but if you have it, you might as well enable it for yourself. You can look at every address of everything. So let's say you wanted to break at this SCSI module for, I don't know, remove target. You look at the call sims and here it is, and here's the address of the base of the function. So you could just break there in GDB, and then when you run something with it, it'll just hit your breakpoint when you're running whatever SCSI remove target for this driver. So that is a very nice file. A lot of times during CTFs, you won't be able to view this because they don't want you to have info leaks. However, you're debugging. You can just give yourself root. If you have root, you can read this file. So you should just give yourself root in the init script and make your life a little bit easier, I would believe. Especially for like developing your exploits. Yeah, also when they load drivers in, like character devices or block devices, they get loaded in last. So they'll be at the bottom of all these. So like this SCSI mod in bracket means that it's loaded in as this driver for SCSI mod. And this is the tail. This is like the end of all the symbols. So it makes it a lot easier if you just run tail, because generally you'll find what you're looking for at the bottom, I believe at least. So I think that'll make it a little bit easier there. How to interface with the kernel. This is the hardest part, or at least when I started, this was the part that really confused me more than anything else. But then when you look at it, it kind of makes sense. Generally, you're going to be using syscalls or drivers. Like I said, you can also do sockets, file systems, memory management, all these things. But in CTFs, usually it's easier for them to just make a driver and give it to you, because then you can just throw the driver in Ghidra, and you know the bug's in there. If you give it like a whole customly patched like kernel, like it's going to be a lot harder. Drivers usually are in either dev or proc, depending on what type of driver they are. And they are also character or block devices, which depends on how they're read data, but that's not too important for what we're going to be doing. Basically, drivers are just like really cool files that work at a very low level. So when you like work with a file in C, you can open it, you can read from it, you can write to it, or vice versa, however you want to like describe those. You can close the file, you can use mmap to map the file into memory. These are all things that you can do with files in C. So you can also do all these with drivers. And the drivers have these custom functions that they create that take place when you call these things. So like if you read from it, if you write, if you open it or release, these are created in this struct called file operations. And this is like the meat of where you're going to find the bugs, is like the reading from the device or the writing to it are going to have some issue usually where you can like find a bug. And you control the arguments to those pretty well too, like with lseek to like the starting position and the data you want to write to it or the address you're going to read from it. These are all things that you control in Userland. Drivers also have these things called ioctls, which we might have learned about in OS. I don't remember if I learned that in OS, but it stands for like IO control. And these are basically really open-ended other things you can call. I mean, I'm sure they have a better purpose, but my way I see it is usually you can pass a struct to it. And I mean, is there another way to pronounce it? I think it's ioctls. I know that's probably wrong. I call them ioctls. And then, yeah, generally, like you pass a struct to it. IOCTL. Yeah, IOCTL is a little better probably. I speak fast with my ioctls, but I'm gonna actually keep that in mind now. Generally, thank you. I was like, it looks like it, but these things generally take structs as an argument, and part of the struct could be like a number, and then it's like, oh, if you send this number, call this function. If you send this number, call this. And it's like a big switch usually. So while IOCTLs or ioctls have like, the main function is basically to implement stuff that's not just reading or writing, from what I can usually tell. And they have them that are locked or unlocked. Yeah, they're IO controls is what it does. So like you can be like, I want to, generally they have a really specific like struct that they take. So part of the struct will be like a number, and then they'll have some other data elements, and then it'll go into like a switch of like what type of data you're sending. So generally that's really like implementation specific to whatever the device is supposed to do, especially for stuff like keyboards and mouses. They take whatever sort of packet they want to send across the USB. Types of kernel bugs. Like I said in the one part, like the userland and kernel both have stacks and heaps. They both need their dynamic memory allocation through the heap because of the fact that you could be working with large amounts of data. And they both need the stack for like function calling and recurrence and all of these things as well. However, the stack is also tied to the thread for each process because of the fact that when you call a whatever kernel function, you need to know how to return back to the actual user mode because it's going to finish eventually. And I'm going to go more into that soon. There's generally one task that you're running, which is like your PID or process ID. And then each task can have multiple threads based on your forking or anything like that too. And that kind of becomes important in the kernel because there's a task struct and then there's also thread specific structs. There's also other types of bugs as well, like integers, array out of bounds, format strings, all these different things. However, they're all exploited a little differently. The stack, like I said before, involves context switching when you're going between userland and kernel mode. There's not just like a smooth transition. They have to do something with this like interesting struct that I'm going to get into. The heap is annoying in the kernel because it's not like one process is touching the heap like it is in user mode. There's like all of these different everything running at one time, and they're all creating structs on the heap and freeing structs on the heap and everything. So it's not like you can just predict, oh, right when I run this, I think my chunk's going to be exactly here in the heap. That's a stretch. I mean, maybe you could groom it a little bit, but that's still definitely a stretch. I mean, the actual like heap mechanisms itself are definitely more simple. I'm going to be getting into the freeing and how that works with the caches, but the actual usage of the heap is not super predictable, I don't believe, just due to like these timers that are running at all times and all these other functions that are being called and any other programs running. There's just like more happening with it. The actual like mechanism itself is like very nice as far as like the SLAB and SLUB. And I'm going to be going into those too for sure. First, like it's important to recognize where the bugs are for these. But yeah, like the kernel doesn't take standard in and standard out, but like they have to get data somehow. And that's where these interesting functions come in. There's one called copy to user, and that takes a pointer in kernel land and a pointer in user land, and then also like a size to copy, and it just moves this data between the two contexts. Copy from user does the exact opposite. It takes some user land pointer and some kernel pointer, and then copies it the other way. Then there's mmap, which you can use. It underlying uses this remap PFN range, and basically that will help when you want to like have a large memory block that is in both user land and kernel land. So that is another one that you might see a lot of drivers have mmap handlers. So if you call mmap with the driver, it does some specific stuff based on the address in your mapped region, sort of like a DMA device. So that's another thing to keep in mind. But generally, copy to user and copy from user, they do what they say. Like they'll copy data to the user or from the user to the kernel. And these are like the general like starting points of where you have control besides the arguments. Okay, kernel stack overflows. If there's a buffer on the stack, and if you can copy data in with something like copy from user, I don't know, put to user, or stir copy, or any other way to get this data from the user to the kernel stack, then you could still overflow the buffer. It's not like there's more like specific checks necessarily for what ret does. Ret still does ret in the kernel level as it does in the user level. So stack overflows are still definitely a feasible attack. However, I mean, I've seen stir copy happen in kernel drivers. I don't know why it's there, but it is implemented technically. However, where do you return to? It's not like normal ROP where you're like, okay, cool, let me find the system in this kernel's libc. Because kernels don't have a libc. They don't have these other things that we're used to seeing. And they also don't have just like a bin.sh string that you can find really easily. I'm sure it exists. So how are we going to also get back to userland? Like when we're done with our ROP chain or our shellcode or anything we're doing, we want to continue running our program because the goal is to have our program running as root, and we can't be running as root if we can't even get back to using our program. And then also like stack canaries are still a thing in the kernel sometimes. These are still things you want to watch out for when you're running a stack overflow in the kernel. Is you might have to leak a canary or leak some other stuff like a base of KASLR or things like that. So like it's very similar in layout, but the exploit is just massively different. So that's when this attack called ret to user comes in, or at least that's what I usually see it called. If this only works for like kernels that don't have smap or smap, which I will get into later, these are basically just like mitigations to make it where you can't run certain code on certain pages and things. But if it's an old kernel that doesn't have these, you can do this thing where you directly return to user space from your kernel. And what I mean by that is you can run code that you put in your user space binary at a kernel level. So people usually call this like shellcode that the kernel runs. It's kind of interesting because it's like C. So I guess it is technically shellcode, but it's very fun to write shellcode in C functions instead. We can find some important kernel function addresses in proc call sims like I was mentioning. And then we can also define these function pointers in our user space code. Generally, the good way to do this would be to find out where this commit creds function is, and then find out where prepare kernel cred is, because the general way to turn your process into the root level is to call prepare kernel cred null to create a root credential structure. And then commit creds just puts that into your currently running process. So generally, if you call this commit creds prepare kernel cred null, this is basically like the win function if you're doing like a CTF challenge. This is your end goal is to get root. And this is a very nice, small way to get root. So like you can't call these from userland because of the fact that these happen at the kernel level. You can tell because it starts at C0000000. That's where the line is basically between kernel and root between user and kernel for 32-bit binaries. But you can still call these if you're running it in kernel mode. You can just ret to wherever they're located in user space and then call these function pointers here from your binary in the kernel mode. So that's a very common attack path that people used to do. So, but we still want to go back to user mode eventually. Even though we're running in our binary, we're running in the kernel mode. So we can't just call system bin.sh or anything nice like that. So how do we get back to the user mode? How do we go home? The best way to do this is that there's this thing called a trap frame. And this trap frame has these 5 things here. It has an instruction pointer. It has a code segment. It has these like normal flags for CPU flags. It has whatever you want your stack pointer to be, and it has whatever you want your stack segment to be. And segment basically is like a way of segmenting memory. So you just need to like say where you would just probably copy it from what it is when you're debugging. But this basically says that you want to return to your userland code and userland stack. Normally, that's how it works on a kernel. The last ret instruction is called an iret. And it'll pop all of these and then be like, okay, cool. We're going to set the stack to this stack pointer and the instruction pointer to this instruction pointer. Then we're going to fix up the flags and segments and all. And then basically at this point, you're going to create one of these in userland memory. And then when we're finished with our kernel payload, we can move our stack pointer to this trap frame that we created in userland and call iret and fix all of these registers for ourselves. Generally, you want to prepare this before your device is called. So you can just sort of pop all of these registers into your own data segment or BSS in userland. And then you pivot there. And then when you do your iret, it'll just fix it all back for you. But you'll probably want to change your instruction pointer so you can actually like call something useful. So you might as well just make a system bin.sh function for the instruction pointer. Stack can stay the same. So this is generally how you go from kernel mode to user mode. And it's not super confusing. So this is like a code snippet of how this would actually look when you're running it. There's this trap frame, which is just the instruction pointer, code segment, flags, and this is also in 32-bit. And the stack segment here. So something that you're going to call before your actual like device call is this prepare trap frame call. And what this will do is it'll basically get all of the flags, the code segment, the stack pointer, the stack segment, and it'll put all these into this trap frame struct you have in memory. It'll also set the instruction pointer to launch shell, and it also probably fix up the stack for you if you want to. And then when you return, your kernel payload is going to call this commit creds prepare kernel cred 0, and then it's going to basically pivot the stack to your trap frame and then call iret, which will pop all of these things from here and fix it for you, and then call launch shell as a user, which is now a root user thanks to this kernel call. I ripped all of this code from this this pwn from Seesaw CTF 2010. I saw someone had these scripts, and I was like, this is a really clean code. It looks better than my code. After this, there's the array out of bounds. This is another very common attack type. Basically, you could have an index of your array that you control, and if this is not checked to be in your array, you could basically write anywhere in all of memory as just an offset from the base pointer of your array. If it's a smaller out of bounds where you can maybe like overflow a few things, generally it's not the greatest primitive, but sometimes you can turn that into a full arbitrary out of bounds. So this is basically a scenario that might happen. Let's say you had like a name buffer on the stack. And then let's say you had a char pointer right after it that was kmalloced or anything like that. And you had an overflow in this buffer, just a small one. If you overflow this char array pointer, you could basically set the base to whatever you want. And this is another good way to get an arbitrary read-write, which is very common. And you don't even need a large overflow. You just need to overflow into this pointer. You don't need to even hit the red address. So in userland, this would be like golden. You could overwrite the global offset table. You could overwrite the destructors. You could overwrite any function pointer in memory that you really wanted to touch. But in the kernel level, it's different. It's still kind of easy, but the goal is a lot different. If we have this arbitrary read-write, we might as well find our user space task, because these task structs also exist in kernel memory because it manages processes. So if you could arbitrarily read and write, you could do a bunch of writing until you find out where, or I guess reading until you find out where your task is in memory. And then you could just override your credentials in there. That seems like a really nice attack plan. You don't have to change the instruction pointer at all. You don't have to call commit creds. You don't have to set up a fake trap frame for your iret. You can just directly write your kernel struct to make you root. That seems like a really good idea. This is where this task struct comes into play. Basically, each user space process is stored in this task struct structure. This includes a lot of things that are properties for whatever userland task. There's a com string, which is just the name of your running process. It has your process ID. It has paging information through this memory management struct. And then it also has this one that's this __RCU cred struct, which is amazing. Basically, this is a pointer to a bunch of ints, and they're like, what is your UID? What is your effective UID? What's your group ID? So these are definitely nice things that you might want to play with here. They're all page aligned too, which is very nice. So what you can do is start at a low page, just read big chunks of data through each page, and then try to find your process name. And if your process name is in that chunk and it looks like what you imagine a task struct could look like, you can just find your cred struct and then write a bunch of null bytes all over there. Usually I use this function called prctl to set my com string to something that's really unique, like just 10 random bytes, for example, because I want to make sure that I'm not going to accidentally find a process that I think is mine and it's not, and that would be kind of annoying. So if you set your com string to something unique, you're going to know when you hit your process, because that's your com string there. Just write a bunch of nulls over your ID, over your group ID, over your effective UID. And then when you run system.sh, you got a root shell. If you want to verify, you can run get UID from user space to make sure you're actually root. But if you do this method, you should generally be root after leaking your task struct, leaking your cred struct, and then filling your cred struct with null bytes. That should help very much. Okay, there's also this thing called the thread info struct here. And this is interesting because I didn't learn about this attack until recently, but this is stored on the stack. And it's stored on the base of the stack. So like the lowest memory address of the stack is this thread struct. Kernel stacks are linked to the userland program that called them with this thread struct. Like that's how it knows that this thread in userland is where we're trying to return to. And it holds just a little bit of information about how your thread works. So each thread has this kernel stack for what it needs it for. However, like any sort of thing that's on the stack, if you do enough recursion, you can slowly fill up the stack. You can keep subtracting the stack pointer over and over and over again until you overlap with this thread info. There's no reason that it'll try to block you. It doesn't check. So you might want to just recursively call a function until you hit this thread info. And then there's this really interesting block that I found out from this John Oberheide talk. And it's old, it's from 2012, but it's new to me. And it's called the restart block. And basically, if you fill up this restart block with your function pointer to your shellcode and user space, and then you just call syscall with this nr restart syscall, it'll try to look in your thread struct for your restart block and call the pointer for the actual syscall. But if you fill that pointer with your shellcode, you can just run stuff in user space and then iret and then shell and be root. So that's another really interesting way to get roots. The other thing is that this thread info does point to a task struct. So if you can leak parts of this, you could leak your task struct, and it might make your life a lot easier than just paging through all of memory looking for it if you do have ASLR. Okay, the kernel heap is a little different than the userland heap. It's a lot different than the userland heap. Basically, it has the same purposes as the userland heap, but it's just like differently allocated in memory. Basically, it has a k-malloc instead of malloc. It has a k-free instead of free, but like it's very obvious which one each does. And it's still there for this dynamic memory allocation. It's for when you need a struct or an object or something and you don't have room on the stack, but you need to have it somewhere in memory to use it later. Basically, the one thing that makes it a lot different is that the chunks are all the same size in the same cache. So for example, if you have a cache size of 1024, you allocate something that's slightly less than 1024, it'll go into this cache. And if it's smaller, it's not like it's going to make a smaller chunk. It's just going to make a normal sized chunk and not use all of it. So that's a very interesting part of how this works differently. This proc SLUB info here is a great file because of the fact that it has information for all of these different caches. You can look at here's this cache and the usage and how many are free and things like that. I don't really know how to read it, but I mean, it's cool. I feel like I used to know how to read it, but this is like a good way to like see heap usage. Because sometimes when you're doing a heap exploit, it's nice to use a cache that's not commonly used because it's not as unpredictable. Like this 8192 cache does not have much happening here. Like there's like only 94 chunks. So there's not really like a hard way of like figuring out which one are you going to use or anything. So compared to this 64, which has a lot going on. So that's something that you might want to take into consideration when you do a heap exploit. There's also these different types of heaps. It used to be SLUB, and then I think SLUB is the one that people use now, and SLUB is a lighter weight version of what's happening now pretty much. But basically, they're similar enough from an exploitation standpoint. The implementation's a little different, but they have a similar free list. They have a similar structure to how they're used and everything else. But the main big thing is that rather than the complicated fast bins or small bins or large bins, each of the chunks contains one pointer to the next free chunk in the first keyword of the thing, the first pointer. So it's just one singly linked list of each in that cache. One will point to the next, and that'll point to the next free one, and so on. And because they're all the same size, there's no need for metadata. You don't need to have a size packed above or like a previous size or anything. You know all the sizes. They're all the same size. So there's not this normal block between each heap that's just a bunch of zeros and then like a size. So that's something else you might want to keep a look for when you're doing exploitation, because that means that there's a very good chance that you're not going to have null bytes between your two adjacent chunks of memory. And that's something that is definitely useful sometimes, and I'm probably going to go into why a little later. Then there's this it's not easy to manipulate the free list like it is in the userland heap because of the fact that, like I said, there's so much happening and there's so many chunks and there's just a lot going on in this memory. But the main thing is that you can spray the heap is what it's called. And like I say here, you're not going to be doing much heap grooming of being like, I'm going to allocate one struct and then this process frees a couple and I'm going to have one. It should be here. Generally, it's more, okay, I have an overlap. I'm going to make a bunch of chunks and see if any of them hit this new overlap or anything. Let me see. The best way to exploit a kernel heap is usually to have a use after free or two overlapping chunks in a cache. That's pretty standard for heap exploitation in the kernel because there's not like the sizes. You can't do the interesting like overwrite and have two chunks fit in one or anything. It's very straightforward in the kernel level. So a use after free is very common, but in case somebody here doesn't really do like much coding yet or anything, I'm going to go into what a use after free actually is. Basically, you might have access to a pointer to a freed heap chunk, and then you could still do operations on it after it's freed because you still have this pointer that you can use. So for example, let's say you have a heap chunk that's a character array in memory, and then it's freed, but you still have this pointer to it, and then you can treat it like it was never freed. Then you could still do read and write operations to overflow data on this chunk, but it's not your chunk to use anymore. It might be a struct now. It might be some other program using it for something else. So that's a very common exploit problem, and that's something that is very great in the kernel level to use. This is generally good because of this low level thing of type confusion, because if you see like that this chunk and you treat it like a character array, but it has pointers in it, especially function pointers, you could overwrite your function pointers in that struct with your own characters because you're using it after it's been freed and reused by something else. So this type confusion is something that'll help a lot. Okay. Use after free and structs. Often the best way to leverage this use after free, like I was saying, is that you want to overlap it with some other kernel struct that's in the same cache size. Generally, you can read from your fake array, if it's like a character array, to get kernel leaks because these structs often have pointers, whether it's a pointer to a heap, pointer to somewhere else in the kernel. And then you could also write to this fake character array to overwrite these function pointers or any other sort of data. Some kernel structures have some like really good and well documented ways to attack them if you do have a use after free. I think these two are the ones I see them used the most. This one's some timer fd underscore context, which is in the kmalloc 256 bin size or cache size. And there's this timer fd tmr proc function pointer, and if you overwrite that, you could get rip execution. Technically, it's in another struct, so you want to point that to something else and point that to your code, but that's super useful there. This other struct that people use a lot is this TTY struct. There's also TTY file operations. It also points to the file ops, and those have all these function handlers for reading, writing, IO controls, all of these things. So if you get an overlap with a character array with your TTY struct, not only do you have these function pointers for reading and writing, but you know the arguments that are getting passed to them because of the fact that you're calling these reading or writing on this TTY from user space. Generally, like you can just create TTYs through this thing called dev ptmx and then just read or write to them. So that's why this TTY struct is a very common thing to exploit. There's also a lot more in this great article here by Pointer Die, and they go through like all of the different ones for basically each different cache size. So sometimes you might not be able to make a chunk of whatever size you want, and you're limited to whatever structs fall into that cache. But there's a lot because the kernel is very, very complicated. Like I said before, it's a lot easier to do heap spraying than heap grooming in the kernel because there's so much going on. So if you're trying to get use after free, I would recommend making just a bunch of TTYs, for example, and then checking your structs to see which one you overlap with. I think that's generally easier than trying to do one and hoping that it falls perfectly into place, because that's not likely. Like I was saying before, the free list is stored in the first keyword, and that points to each next free chunk in memory. So that's pretty normal. However, if you have a very small heap overflow, you could overwrite this first keyword. You could overwrite this heap chunk pointer. The larger size structs tend to be less randomized. So I've seen, oh, okay. I've had a lot of issues with the timer FD one, but I guess that's probably because it is smaller. So that is good to hear that. The bigger ones, you won't have to do as much spraying. You could generally put them where you would think that they should be. So thank you for that one. Yeah, if you have a small overflow and you can overwrite this first keyword alone or part of it, if you have your in-use chunk and then right below it is a free chunk, you could partially overwrite the free chunk so that it points somewhere else on the heap, for example. So if you do a partial overwrite of like maybe a null byte or something like that on the first bit of the free bin pointer, there's a pretty good chance that that could now point to a chunk that's already in use. So like the use after free, you get a similar situation where if you allocate a chunk and it takes one off the free list, which is now overlapping with some other chunk that you're already using, you could have two chunks that you control that are different things. One of them could be a character array, one of them could be a TTY struct, for example. So this is another good attack. Pretty much, yeah, you want to check the kmalloc size and find a struct that works for that again. Same sort of situations to use after free, but basically you're just faking this linked list, the singly linked list, to point back to your struct in memory, which is also kind of heap spraying in a way, but it's pretty effective. I did this for this shared house challenge for ASUS CTF. That was a very interesting challenge. It was also made by Pointer UDI. It had a sort of small overflow in the heap, and you could attack the free list. But now there are these mitigations that I found out about last night, thanks to Kid of Arcrania, that are free list pointers being like mangled and XORed with the cookie. So basically, if you do a partial overwrite without leaking what this is, it's probably not going to point somewhere good because of the fact that it's mangled with a like randomized cookie in memory. And because of this, you could still exploit the free list, but what you have to do is you have to leak that cookie or leak that forward pointer with the cookie in probably a couple of those, and then sort of XOR out the cookie when you know where you actually have a heap leak so that you can sort of like recover it and then partially overwrite with your own sort of exploit. So like the exact offset where the heap chunk will point to might be bad. Yeah, that is true. Awesome. Thanks for watching so far, Gabriella. Yeah, the exact offset where the heap chunk will point might be bad if you do just a partial override, or if you only have like a null byte override. But if you leak out the cookie and leak out where it's actually supposed to be pointing, there's a good chance where you could control it if you have like another heap leak or something like that. It's definitely a lot harder, and it's definitely not something that you'll want to do if possible. Generally, you might want to actually like find a better bug if that's possible, because this free list is pretty annoying if it is hardened. The next big one is called race conditions, and these are very common in the real world, and they're not super common in CTF. So I saw one very recently in Seesaw, and I didn't find it because I don't look for race conditions enough, but this is another interesting type of attack here. Basically, when you run programs, sometimes it assumes that certain operations execute sequentially in like a certain order without anything happening between them. So like, for example, first it might check if this file is a certain size, And then if it fits a certain size check, it will read the contents, for example. That's definitely a thing that could happen. However, in a race condition, and this is just a userland example, you could probably try to change the size with a different thread after it checks, and then read more in than you're supposed to, because it passed the check, but then it was changed before it was actually used. Kernel race conditions are pretty common in CTFs. Userland, not so much sometimes. Yeah, like I was saying, you're going to use pthread or fork to create two operations happening in two different threads at the same time. And then you sort of have to do a little bit of brute forcing and hoping to get the exact right sequence of operations to happen in order. So here's an example. Let's say you made a chunk on the kernel heap with an ioctal or IO control, and then you have two threads. Thread 1 could call the IO control to write to this chunk, and then this driver for the first thread will check if it's in use or not. And that, referring to the heap chunk, like if it's freed or not. I don't know how it checked. That might be a thing. And then after this check passes, and it's like, okay, cool, this chunk is not freed, we can use it. Thread 2 could be like, actually, I'm going to free the chunk right now. And they free the chunk really quick. And then after that, thread 1 is like, we already passed the check, we're just going to write to it. So this small little window there is where these race conditions occur. And that small little window leads to a lot of bugs, especially in the real world. Usually they're called time of check, time of use bugs, where it does a check and then it uses it, but that check is no longer satisfied by the time that the bug is used. And that's pretty popular. Here's one example that's pretty common. It's called a double fetch. Basically, this is like probably the most common class of race conditions, I would believe. Usually what happens is the same data is copied from the user to the kernel mode with like copy from user twice. So the first copy will be for some sort of a check, and then the second copy is actually using the data. For example, it might copy a struct and be like, okay, cool, the first keyword is a small size, we can read this much. And then it'll copy it again and then get the size again and not check it because it already assumes it's right. And that window there allows for you to change it in userland. And then when it copies that userland memory over again, you could write way more than you did before. So that's definitely possible. Yeah, this could be an issue because the data in userland can be changed during this window. Man, I have so many typos. For example, like I said, the integer for size could be copied and checked. So this is pretty common in CTFs. I've seen this in a lot of them, and usually you should always fetch once and save the data. And then when you're doing stuff with it, just use the same data. You don't want to copy it again. So double fetches are pretty avoidable if you're doing actual kernel programming. Yeah, there's a few interesting challenges for stuff like that. Then here's some just random stuff that are definitely possible in the kernel level. Print K is the kernel's version of printf. And yes, it can also have format string bugs. It's not perfect. There's integer underflows and overflows and signedness issues as well with those integers. There's like jump table out of bounds, which are pretty similar to array out of bounds, but it's possible that there's a faulty jump table for a switch, for example. And that's really calling out one specific challenge, but I don't want to say which one in case anyone tries to do it. There's logical bugs, of course, where it's just the program isn't expecting certain cases and doesn't really handle them correctly. There's null dereferences, which are very old, but there used to be a thing where you can maybe have a pointer fail or be uninitialized or have malloc fail or something and have it be a null value. And then it tries to call this null value. However, in the old times, you could mmap a page at page 0 in userland and put your kernel shellcode there. So that was a pretty common class of bugs, was these null dereferences, but now you can't actually mmap at 0. You have to start a little further down because of this issue, probably. Another common one is that files are handled by the kernel. File opening and closing can lead to these kernel file structs, and fput closes the file struct and frees it. However, if you have a double fput through certain code paths, for example, you could free the file twice and then have overlapping file structs in the kernel, which is very interesting. And apparently it's relatively common. I've read a few Project Zero articles, but if you have a double file puts with this like overlapping file, you could do interesting things where you can read or write to files you're not supposed to because of having sudo operations or sudo operations to open this file, and then you just do your own else so you can read while this is happening. So you could execute past wd to change your password, and it would open up the etc password or shadow file or something like that. And then while that's open and waiting for input, you could have your other one that's overlapping just read all the data out because they're both the same data in the buffer. So that's another very interesting type of bug. Okay, now I'm going to go into a few like tips and tricks and things that are actually like going to help a lot if you're trying to do any sort of CTF kernel exploitation, especially in 2020 with all the mitigations they have. C or Python. C is just better for kernel exploitation. It's easier to work with file descriptors and IO controls. There's less overhead. You know exactly what's happening when you run a program in C. Generally, I think people always develop exploits in C. Also, you won't always have a Python interpreter on a remote server. You could probably compile your Python, but then you have to do it statically as well. So you might as well just do it in C. Another thing that I use is this amazing thing called standardint.h. Basically, it has a bunch of data types that are like uint 64_t, where you know it's 64 bits and it's an unsigned integer. And it makes it easier when you're doing kernel exploitation, because when you have these structs, you want to know exactly that your data is the right size. So if you look in Ghidra and see, okay, the first 64 bits are a index, you can just make a uint 64t as an index, and then you know it's the right size. So I would highly recommend using this if anyone does kernel exploits. Awesome, see you around. I'm going to try to speed up a little bit because of the fact that it is running late, but I'm going to make sure to keep the slides online too. How do you actually get your exploit to this remote VM? Usually you don't have GCC or libraries or a network or anything like that. So what's generally best to do is to base64 encode your whole entire binary into just base64, and then just send it chunk by chunk. So this is a good script here at this link to actually do that, because you start your session with SSH and then just echo base64 append to a file, and then just base64 decode it. If you're going to be doing this, you could make a very large script because they don't have libraries. So you might want to use a smaller version of the libc libraries. They have diet libc, UC libc, MUSL is another good one. glibc is massive. You don't realize until you statically compile and base64 encode it, but it is very large. So you might not want to use it. A lot of these involve compiling it in a CH root. I believe that Claire gave a talk last year on embedded systems, and that involved CH roots too. So that would be a good thing to refer to. For local testing, you might just want to put your file in whatever init ramfs you're using. If you have a CPIO, you should make a little script to compile and uncompile it, and then put the exploit into there. glibc is massive. If you look at a comparison chart between all of them, glibc is like awkwardly large compared to everything else. And for good reason, I guess. It does a lot of very specific checks, but it's just too big. If you have an ext file system, you can mount it in a folder and then put the exploit into that folder, and then it'll just be mounted and compared to whatever ext2 file system file you're using with QEMU. And while you're doing this, like I said, just give yourself root access in the init script. It'll make it a lot easier on you. Yeah, it has a lot of features, but nobody knows about those features, especially for like printf. I don't know. I feel like printf is too complicated and not important in a lot of cases in the real world. especially in glibc. $. $sign is nice, unless you have fortify source and you can't use it. Some of those QEMU extensions are fancy. I mean, yeah. The problem with libc is that there's so much defines and not defines. It's really hard to tell by reading the source tree how much is going to be used when you compile it. So that's another issue that I see, is that it's not really nicely translatable, I guess. User fault FD. This is another really great script for running race conditions. Basically, it's a C function, and it lets you create a handler for page faults. So what that means is that when you try to access a page in memory for like the first time when it creates this page fault and it's non-swap, it'll break into this handler that you created in another thread and be like, what should we do before you can access this memory? And it lets you kind of put whatever sort of code you want, and then you send it on its way. So what this means is that it's great for race conditions. So let's say that you created, okay, this example here, yeah. When you have copy from user to put data from a page into some kernel heap chunk, you could have this user fault FD handler for this page that will free this kernel heap chunk or call some other functions on this driver, maybe change size, maybe like change the data inside or something like that, and then you forward it on. So this is great because it basically makes a lot of race conditions 100% reliable. It means that when you hit this point, basically it'll just keep going and like let you do whatever you want for whatever amount of time you need, and then forward it on. There's a little bit left. I'm going to go through the next couple of slides. The last little bit are examples, but we don't really have to go through the examples altogether because of the fact that it is running late. So I'm just going to go through the 3 main types of mitigation techniques, and then it'll be good. And I'm going to go pretty fast through them because these are like relatively complicated. Yeah, these are the main mitigation techniques here. I'll go more into them in each slide, but SMAP and SMAP are the main ones. And then KPTI is kernel page table isolation, which is really interesting because it means that user space is basically non-executable in any way. And you can't even just iret. You have to call this special trampoline function, which will fix it for you, which I'll go into. Kernel ASLR is basically like Userland ASLR. It means that you don't know where the kernel base is or anything. Like you don't know where the heap is. It could be anywhere. I gotta see that meme. I'm curious. And then the randomized structure offsets are another thing where it moves different parts of the structure around so that like it's not the same. So like if you have a task struct and you're like, okay, com is the 20th word. If you have randomized structure layouts, it's not necessarily the 20th word. So that's another interesting thing that happens in that you can compile into the kernel. Okay, bypassing the SMAP, this is where kernel ROP takes place. So basically, if you can't run the code in Userland, you could still use a ROP chain in Userland for SMAP because you're not executing the code. It stands for supervisor, let me go back. Yeah, supervisor mode execution protection. And then SMAP is more strict and it's supervisor mode access protection, which means you can't even read it. But for SMAP, you can't execute it, but you can still read it. So you might as well write your own ROP chain into user space. To get to your ROP chain, VM Linux is massive, so you basically have whatever ROP gadget you want. Usually, it's best to use some exchange, RAX, RSP, or something like that. A lot of times they have some exchange, some static value that you can pop into RAX to or move in, so you can mmap your page wherever you want in user space. You have a lot of options of where you want to put your ROP chain. Generally, the first thing you want to do is unset this 20th bit of CR4 because that's what determines if you have SMAP enabled or not. So you can actually unset this to disable it and then jump into shellcode in Userland, do the ret to user attack, which is very nice. However, if KPTI is enabled, this doesn't work because there's other important things that you have to do. I'll go into. Here's an attack people used to do, which involved the VDSO. Basically, you could find this in the user space program and then find its equivalent in the kernel because it's just mapped between the kernel and the user. And then you can patch whatever code into the kernel that you want in this VDSO because it was kernel writable. And then if you call get time of day from user space, it'll call whatever's at the get time of day function space in the VDSO, which is now your shellcode. So that's another attack that people used to do. However, that was patched because now the kernel cannot write to the VDSO, which should have been true before. SMAP. This is a little harder because this means you can't even access userland data. However, you could still make a ROP chain in the kernel. Like if you had kernel heap where you could put a bunch of characters, you could write your own ROP chain there. And then if you had a leak of that, you could just have that be your pivot into the heap. However, if you do have a read-write, you could do whatever you want still because you're not trying to execute userland code. You can do the data-only attacks of actually changing your root, changing your cred struct to root or anything like that as well. And as long as you're not actually touching RIP, you're not going to have any issues with SMAP or SMAP. Again, this is also a bit of the CR4 register, so you could use your ROP chain to try to fix this as well, which is nice to do. The other way to bypass this is something called ret to dir, which stands for return to directly mapped memory. This one, you can abuse this thing called the fizz map, which basically is a mapping of these synonyms, which is basically like all of the userland pages have some sort of a mapping in kernel land. So if you have this thing here, you could basically create a page in userland and then find its synonym and read or write to it from the kernel directly. So that's another interesting attack. And this is a little harder to do, especially with the leaks and stuff you need to do. But for example, if you mmap a bunch of pages in user space, chances are it's not going to be too hard to find the synonym. And then you put whatever shellcode into this user space mapping and then run it in the kernel space one. So in the userland, you could be like, let me put in the get whatever, get creds, commit creds, everything. And then on the kernel land, just call it as a function pointer and you're done. And you don't actually change to user mode. It's still kernel level because it makes a kernel level copy. You could also get the task struct into userland possibly and get leaks from that due to this fizz map. So there's a lot of things you could do here. However, it's no longer read, write, execute. So you can't just execute the fizz map pages anymore from kernel level. So that's not really a thing anymore, but it was very interesting. Okay. Now the last one is this KPTI, which is kernel page table isolation. Basically, if you use this with SMAP, you can't just return to user mode without fixing up some registers and segments like the CR3 register. Because user space is marked as NX, and when you use the CR3 swap, you get different code that's NX and not NX, so you can then actually execute your user space. Because of the fact that kernel functions have to return somehow, there is an actual kernel trampoline function that you can find, which actually will fix up CR3 for you and let you go back to user space. It's very convenient because it'll just fix everything for you. The other way that people used to do before they really understood how this CR3 was fixed was that you don't actually have to go back to user space. What you could do with your kernel mode is you could change the owner of the whatever file you want to read, like maybe /flag, for example. And you can make it readable by all users. Then you could just have your loop or a timer or something that'll just make the kernel hang. And then in another thread, you could just read the flag. And because of the fact that you can do this sys change owner from kernel level, you never actually need your kernel to return to user space. This is kind of CTF specific because in real life, if you were stuck in kernel space, eventually it would have to crash And if it did, eventually the whole entire kernel would restart. So it wouldn't be very sneaky at all. However, like for a CTF, this will help you get the win if you don't know how to find a KPTI trampoline, for example. Yeah, this is the last little bit of like the tips that I'm going to be giving, and then I'm probably going to be wrapping up because I'll have the slides in the Discord. But the other attack that you can do is on this thing called the mod probe path. Basically, this points to a string that is a file name, an executable name. And when the userland tries to execute a file that it doesn't have a normal header, like it doesn't know what the file type is, what it can do is that it can call whatever is pointed to as mod probe path, and it'll run it as root permissions, and it'll hope that it'll fix up whatever issue it is, or at least return a nice error. So what you can do is you can create a userland script to change permissions of a flag to 777, for example. And then if you overwrite this mod probe path with some other weird stuff for whatever this like executable file you made is, it'll run your executable as root if you just try to execute like a bunch of Fs, for example. And if you do that, it'll run it as root, and then you'll have permissions to do whatever you want. So this is another interesting place to store, almost like shellcode, is this mod probe path. And it's also another relatively common attack strategy. So after this, I have a few CTF examples and also real world ones, but it's definitely past time. So if anyone wants, I can just send this link to my Google Slides in the Discord, and you could look through these yourself. It has a lot of different like pages and references and challenge names and things like that as well. So I think that would be a great way to get started. And you can always reach out to me for help too. Would anyone want to see that right now, or is it running late? Because I can always just send this. And also, is there any questions? My bad. Any questions? It's coffee. I always drink coffee. That's my thing. Yeah, I'll save the recording and put the recording on Discord too. I'll find out how to. I'm probably gonna stop recording now.